Hey y'all, welcome back. It's good to see you guys. So today we're going to be looking at solving what we call quadratic equations. And basically what that means is if you've got an equation with like an x squared in it, we can't use the same techniques that we used to solve linear equations. So for linear equations, we do things like adding a number to both sides of the equation or dividing both sides of the equation by a certain number. And those properties of equality, although they still hold for quadratic equations, they're not particularly useful in isolating x. So starting today, we're going to look at several different techniques for how you can solve quadratic equations. Today, we're going to be looking at how to solve quadratic equations by graphing the related equation. Now, we've never graphed quadratic equations before. We've graphed plenty of linear equations before, or graphs that look like lines using slope and the y-intercept, or if it was in point-slope form, plot a point and then draw the line. We haven't really looked at how to graph a quadratic equation. So we're going to start without using any tricks or anything like that. What we're going to do is use a technique that will work for graphing any kind of function, and that is just creating a table, plotting some points, and sort of play connect the dots until we get the whole thing graphed out. Now, the reason why we're going to do that is if our quadratic equation is set equal to 0, then we can just identify the x-intercepts on the graph. In other words, wherever the graph crosses the x-axis, we're going to find our solutions. So we'll go through all that in today's video, and hopefully by the end you'll have a better understanding of how to solve a quadratic equation using this graphing technique. The solutions to a quadratic equation are sometimes called roots or zeros, and they can be found by examining the x-intercepts of the graph. And so basically what we want to do here is we want to first make sure that the equation is in standard form. In other words, it's going to take on this ax squared plus bx plus c format, and we want it to be equal to 0. Okay, so a couple of things to note here is that first, the a value is going to be positive when it's in standard form. So the a value must be positive or greater than 0. Otherwise, if it's 0, it's not going to be quadratic at all because you'll just have a linear equation here. And if it's negative, we want to move everything to the other side of the equation to make that positive. And it will just make life easier if that first term is positive. So two things here. First, it's equal to 0, and then also make sure that everything's on the correct side of the equation so that this first term is positive. Then we want to graph the related function. Okay, so in other words, if we have y equals this standard form quadratic equation, and we plot the graph, when we find the x-intercepts, that's where we're going to find the solutions. In other words, the numbers that we can plug into x to make this equation true. So that's the basic idea here. As long as you understand that we are trying to find the x-intercepts of the related graph, that's really all you need to know. So let's go through some examples and I'll kind of show you how we're going to graph these. Essentially, we're not going to use any tricks or anything. All we're going to do is we are going to construct a table. As you can see here for each of these examples, we're going to put the equation into standard form, and then we will construct the table, graph it out, and then wherever we cross these x-axes, that's going to be where we're going to find our solutions. So not too bad, especially with the use of a calculator, and we will definitely use a calculator here to do this. So let's go ahead and start the first example. So you'll see in this first problem that the a value here is 1, the b value is -1, and the c value is -2. This already equals 0, and the a value is already positive. Like I said, it's +1. So we don't have to do anything to manipulate this equation to get started. The graph that we are going to use to solve this, or what we call the related function, is just y equals x squared minus x minus 2. So it's basically the exact same equation, except we're going to set it equal to y so that we can actually graph it. So this is what we call the related equation. So let's take a look and see what this graph is going to look like to just get an idea first, and then we'll actually construct the table and graph it by hand. So go ahead and turn on your calculators. Looks like I just cleared my memory here, which is good. And you're going to hit the y equals button. Okay, and this is going to be how we enter in the related function, which is x squared. So here's the x button, squared minus x minus 2. So if we hit the graph button, it's going to show us basically an idea of what the graph should look like. Now, you don't really want to use this to plot what's going on down here, down on the graph. You don't want to just sort of like, quickly draw it out. We're going to use the table to do that, but at least we can have an idea of what it's going to look like. Now, to actually construct the table, what we're going to do is we're going to hit second and then graph to access this table function. So notice that it's table's written in blue here, and to access all these blue functions, you hit the second button first. So as you scroll up and down, you're going to see there's a plethora of points that we have to choose from here, but we really only want to pick points that are going to fit on the graph. So you want to focus more so on these smaller numbers, like for instance, -3, 10 is going to be way up here, and that's not going to fit on the graph. Now, if it's slightly off, it might be worth putting on there, but if it's way off, it's going to be hard to plot it accurately, so we're just going to skip those. So let's go ahead and start filling out the table. Now, you might be wondering, how do I know which values to pick? I would just start with the first one that will actually fit. So in this case, -2, 4 will work. So I'm going to go ahead and type in -2, 4. And I'm going to copy the rest of the table out. So, like let's see what the next one is. We've got -1, 0, and we've got 0, -2, and we've got 1, -2, and 2, 0. And the table kind of stops there, but you definitely want to check and make sure there's not any other points that we might be missing that we could potentially plot on there. The more points you can fit, the better, so you get a better idea of what the graph's going to look like. So like, I'm going to go ahead and just throw in 3, 4 as well, even if the table is done there, because I want to see that symmetry. And I want to see as many points as I can on this graph. Okay, so let's go ahead and start plotting these out. -2, 4 is going to be -2, 4 is going to be right about here. Okay. -1, 0, 0, -2, 1, oh wait a minute. Yeah, 1, -2, 2, 0, and 3, 4. So you can see that we have a graph that's starting to take the same shape as this one that we saw in the calculator. So this is looking pretty good. You definitely want to double check the calculator and make sure everything's looking like it should. And then we're going to go ahead and draw out the parabola. Now I'm drawing this with a mouse, so it's going to be a little sloppy, but it should get the basic idea down. Put some arrows on the end to show that it keeps going. One thing I do want to point out here is that look down here. You've got these 2 points that are right next to each other. This is not going to like hit a sharp corner and then just go horizontal straight to the next point. There will be a little bit of curve here. So this entire curve should not have any straight segments. Okay, you should not be like just straight up connecting the dots like with a ruler, but you want to try to show this curvature. Now this shape is different than what we get when we graph a linear function. When we graph a linear function, we get a line. When we graph a quadratic function, what we get is something called a parabola. That's the name of this sort of U shape that we get when we graph a quadratic function. And all quadratic functions will be graphed as parabolas. Now they might be upside down, so they might be like an upside down U, but the same basic shape will hold. In other words, it'll take on this kind of U shape. Now once you have it graphed out, we're going to identify the x-intercepts. So you might notice we've got an x-intercept right here and one right here, okay, at -1 and 2. Those will be the x values that will satisfy this equation. So we don't have to do any funny business like adding 2 to both sides and all that to solve this. As long as we set the equation equal to 0 and identify the x-intercepts, then we have our solutions. So in this case, let me scroll up just a tad, our solutions will be x equals -1, and we also get x equals, what is that, 2. So there's going to be 2 solutions here, and I'm going to write both of them. Now, most of the time you will get 2 solutions, although it is possible to just have 1 solution. Like if this point, which is called the vertex, is right on the x-axis, like if the u comes down and just touches the x-axis at one point and then comes back up, it's possible to just have a single solution. It's also possible to have no solutions. If the parabola comes down like this, but does not cross that x-axis, then we will not have a solution. So we're going to see a couple of examples of that as well. Let's do number 2. We're going to do several examples here until we kind of get the hang of this. So we have x squared plus x equals 20. Now in this case, notice this is not equal to 0. So we need to make sure that it equals 0. We're going to do that by subtracting 20 from both sides. So I'm going to subtract 20 from this side, subtract 20 from this side. Let me kind of make this look a little nicer. And when we subtract 20 from both sides, if I can move this over, what we get is x squared plus x minus 20 equals 0. Now that we have it set equal to 0, we can actually work with this, okay? So just make sure that your function's always equal to 0. The equation that we're going to graph now is going to be y equals, and then that exact same expression, x squared plus x minus 20. So that's what we're going to put into the calculator. So let's go hop back over here to the calculator. Oh, I just realized you can't see anything I'm doing here. Let me move this over. My bad. There we go. Okay, so just to recap there, sorry I covered that up, but we're going to subtract 20 from both sides, which gives me x squared plus x minus 20 equals 0, and then we're going to solve the we're going to graph the related function y equals x squared plus x minus 20. So I'm going to go back to y equals in my calculator, and I'm going to clear out number 1, and I'm going to type in number 2 here. X squared plus x minus 20. And let's take a quick look at the graph. Okay, so you can see this one's going to go a little off the grid here. So that's a little unfortunate that we're going to not be able to fit it on the graph. We're going to do the best we can, but remember that the important part here is the x-intercepts. So as long as the x-intercepts are visible, we are going to get our solutions real quickly. It looks like our solutions are going to be 4 and, what is that, 1, 2, possibly -5, maybe around -5, not super clear, but we're expecting approximately 4 and -5 for our solutions. And when we graph, we're going to be kind of looking for that too. So let's look at the table. Now, we're not going to be able to fit a ton of points on here. Yeah, this is going to be a little tricky. Let's see what we got going up here. So obviously -952 is not going to fit. Let's start with, okay, -610 is kind of going way off the page there. But I'm going to at least estimate where that is just so we can have a better picture. We do see our solutions right here, -5, and I believe, what did we say it was, 4? Yeah, 4. So we can kind of see what our answers are going to be there. And once you realize what you're looking for, the graph almost becomes kind of pointless. But let's construct our table. And I guess, what do I want to start with here? You know, I'm not really sure. Let's just start with -6, and we'll just kind of go from there. So, so let's start with -6, 10. There we go. And then we've got -5, 0, -4, -8. Now, I don't know if it's really necessary to include all these points because obviously most of these are going to be way off the grid. That's kind of don't like that, but kind of I'm going to use what we're given here. -2, -8. Oh, just switched over to black for some reason. That's kind of weird. -2, -18. And then we've got -1, -20. And I just want to kind of work my way until I get back to the other 0. Okay, so we see the symmetry occurring here. So the y-intercept, which isn't really relevant here, but the y-intercept is going to be at -20. And so you can see that vertex, so that kind of middle point, is going to be right in between -1 and 0. And then we've got 1, -18, 2, -14. This is really too many values. You really don't need this many values, to be honest. 3, -8. And finally, let's get that last one, 4, 0. Okay, so this is kind of a mess. But let's see what we can fit on here. -610 is going to be, somewhere way up here. This goes 1, 2, 3, 4, 5, 6. This is 6 by 6. So I'm going to just kind of ballpark that -610 up here. Then we have -5, 0. We've got -4, -8, which is going to be somewhere down here. I'm not even going to bother with these next few. We just know that -3 is going to be way down here, -2, -1, and then we really are not going to get back to this -14 until we get to 2. So I'm just going to plot that. We just know that it's going to come down real far and then go back up. So I'll try my best to do a sketch there, but it's going to look a little messy. And then after 2, -14, we got 3, -8. Oh wait, you know what? I think this was supposed to be -8 right here, right? And up here we had what, 10 as our estimate. So I need to move that over. So we've got 3, -8. Apologize for that. And then 4, 0. And then it is going to go back up here. So really, like, the parabola is going to do, let me just scroll down. It's going to kind of go down and then go way down and then come back up. Now, we don't need to graph all of that, but it doesn't hurt to get a good idea of what's going on with the graph. The solutions here are going to be where we find the x-intercepts. Hopefully you're starting to catch on to that by now. So -1, 2, 3, 4, 5. We've got x equals -5, and we've got x equals 4 as our two solutions. Okay, hopefully there's not too many of those. I kind of like it when they fit on the graph a little better. But those are going to be our solutions for this number 2 here. Let's take a look at number 3. And I'm going to move this calculator over so it doesn't get in the way like the last one. Okay, so we got an issue here, and that is, first of all, it's not equal to 0. And second of all, that leading coefficient is not 1, or it's not positive, sorry. It needs to be positive, and right now it's negative. So what we're going to do is we are going to add x squared to both sides. And what that's going to effectively do is it will move the x squared to the right-hand side of the equation. But what's more important there is that it will make it positive. So right now it's going to look like this. 0 equals x squared minus 6x plus 9, which is fine. Whenever you have an equation like this, you're free to reverse the order here. So like if 0 equals this expression, then this expression will equal 0. And just to stay consistent with how we're writing the rest of the equations, I'm just going to go ahead and reverse that right now. So now we've got the equation equal to 0, and the leading coefficient is positive. So we are ready to graph y equals x squared minus 6x plus 9. Let's cross our fingers and hope that this one actually fits on there. So back to the calculator we go. And I'm going to go ahead and clear that out, or go press y equals, clear out the last one. And the new one is x squared minus 6x plus 9. I'm going to look at the graph just to get an idea. Let's see what's going on here. Oh, okay, good. This one does appear that we are going to be able to fit it, so that's fantastic. So this one will work out a lot nicer than number 2. I'm going to go to the table, and I don't want to plot all these points like I did in number 2. So I'm gonna find some good ones. So like -2, 25, not very good. Here's where the money is right here. Looks like between x equals 1 and x equals 5. So I'm gonna use that for my table. So let's go ahead and input that in. We've got 1, 4, 2, 1, 3, 0, 4, 1, 5, 4, and that's probably good because we're not going to be able to fit 6, 9 on there, unfortunately. Let's see. Let me try to make this look a little nicer here. I know y'all probably wondering, like, who cares if it looks nice? Okay, so let's go ahead and plot these out. 1, 4, 2, 1, 3, 0. So we basically have our answer here. 4, 1. So this is an example. You know, before I was saying that it's possible to have only one solution, and I briefly tried to describe like what that would look like. Well, here's what it looks like. It's when that vertex or that point that's right on this like symmetrical line. Let me try to clean that up a little bit. Can I clean that up? Oh, no, I just deleted the whole thing. So let's just try to draw it again. Let's see if I can get a little curve going there. Oh, that looks a little better there. Tough to use this mouse. But anyway, this parabola only hits the x-axis at one spot. So the solution here is just going to be 3. There's only one of them. And that's okay. It's okay to just have one solution. That's going to happen sometimes. In fact, sometimes there will be 0 solutions. But if you think about how this shape looks, it would be impossible to have more than 2 solutions. So you're either going to have 0 solutions, 1 solution, or 2 solutions. That's it. And I'll go into a little bit more detail on that in just a bit. So let's take a look at that actually right now. How many solutions should we expect in our quadratic equation? So there's possible to have 2 x-intercepts. We saw that in problems 1 and 2. There's the possibility that you have 1 x-intercept. We saw that in problem 3. And it is possible to have no x-intercepts. So when that happens, you either have 2 solutions, 1 solution, or 0 solutions. And essentially what the graphs will look like, and I'm just going to do a quick sketch here, you will have 2 solutions when the graph crosses twice. And we saw that in problems 1 and 2. This is real sloppy, but that's basically what it'll look like unless it's upside down. It's possible to just have 1 solution. So that's when you have a parabola that just touches the x-axis in one location. And it is possible to have no solutions. In other words, there's no value you could plug into x to make the equation true. And when you graph the related function, you get a parabola that never touches the x-axis. So it might be like up here where it's just like slightly above there. It might be way above. But the point is that if it doesn't touch the x-axis, there's going to be 0 real solutions. So just want to make that real clear that you can expect there to be 0, 1, or 2, but never more than 2, and obviously you can't have negative numbers of solutions. Let's look at a few more examples. I think the more of these you do, the better you're going to get at these. And really, you know, I just want to kind of practice getting these into standard form, putting them in the calculator, and identifying the x-intercepts. So I'm going to move a little faster with these next 3 than I did on the previous 3. On this first one, we can see it's not equal to 0, so we need to move everything over to the left-hand side. We want this x squared to remain positive, so we don't want to move the x squared to the right-hand side. Instead, we're going to bring the 3x and the minus 3 over to the left-hand side. So to do that, we are going to subtract 3x and add 3 to both sides of the equation. So we're going to do that to the, what's going on here? Oh. Can't move it. There we go. So we want to take that away from the left-hand side, but we also want to do it to the right-hand side. In other words, we're just going to move everything over to the left-hand side of the equation. So that results in x squared minus 3x plus 3 equals 0. And once we have it equal to 0, we can write the related function that we are going to graph, x squared minus 3x plus 3. This is what we're going to put in the calculator. So let me bring that calculator back up and go to y equals, clear out the equation, type in x squared minus 3x plus 3. I'm not going to bother looking at the graph. I'm just going to go straight to the table here. I'm looking for some points that I can plot, and this looks like a good place to start here. So let's go ahead and fill out this table. We've got 0, let's move this a little bit. There we go. 0, 3, and I'm starting there because negative 1, 7 is going to be off the grid. 1, 1, 2, 1, 3, 3, and 4, 7. I have that right? And we won't be able to fit that, but that's okay. The number of entries in this table doesn't have to be 5 entries. You just basically want to fill as many as you can. So we got 0, 3. Oh, yikes, that's pretty ugly. 0, 3 is not that much better, but 2, 1. I'm sorry, 1, 1, 2, 1, and 3, 3. So it looks like 4, 7 is going to be like slightly above this. So because of the symmetry, we know there's also going to be a point at negative 1, 7 as well. We're going to sketch this out, and it does not appear as though we're going to touch that x-axis, but we want to be sure. So, I said I was not going to pull up the graph on the calculator, but let's just look real quick and just to double check and make sure this doesn't actually hit the x-axis. And you can see there is a little bit of space in between there. If you're not convinced, we can zoom in and see it a little bit more clearly that this does not, in fact, hit the x-axis. So we're going to go and just say that there is no solution, and that's it. There's just no solution or no real answer. Now let's take a look at number 2. Let's move this calculator out of the way. Okay, so number 5. Again, this is not equal to 0, so we need to move the 4x over to the left-hand side, and we can do that by subtracting 4x from both sides. So when we subtract 4x from both sides, we are left with x squared minus 4x equals 0. So we don't have a constant here, which is fine. It doesn't really matter if you don't have a b term or a c term. It's really that a term that's really going to throw a wrench into things if you don't have that x squared. So the related equation that we're going to graph is going to be y equals x squared minus 4x. And that's what we're going to throw into the calculator. And we're going to be looking for those x-intercepts. So back to the calculator, hit y equals, clear out the last problem. Here we've got x squared minus 4x. And we're going to look at the table. Okay, negative 1, 5, that looks like that's going to work. Negative 2, 12, that's a little bit too, that's going to be off the grid. So let's start with negative 1, 5. Now, most of these problems should be set up so that you don't have to look too far for the points, but it is possible that the points that will fit will be kind of a little difficult to locate on the table in the calculator, but most of the time it should be right around 0. So negative 1, 5, 0, 0. Let's see, 1, negative 3. 2, negative 4. 3, negative 3. And just for fun, I'm going to throw in 4. I'm going to go all the way to 5 here. 4, 0, and 5, 5. Like I said, the more points you can fit, the better. So if you go a little past what's actually on here, as long as the points fit on here, then you'll be fine. So let's see, we've got -1, 5. So it's going to be right here. 0, 0 is the origin. 1, -3. 2, -4. 3, -3. These points are probably the ugliest points that I've ever seen. 4, 0, and 5, 5. So we get a nice little parabolic shape. Again, this is called a parabola. So if you ever hear me use that term, I'm talking about this U-shape graph that we get from quadratic functions. Okay, so my solution, this one is going to have two solutions, one right here and one right here. And we can name them. We get x equals 0 and x equals 1, 2, 3, it looks like 4. Okay, so that's number 5. Let's do number 6, and then we're going to look at a couple of application problems. So get this out of the way. Okay, so once again, we got to move everything to one side. So we're going to subtract 2x, and we're going to, here, let's actually make this look a little better there. We're going to subtract 2x, we're going to add 6 to both sides, and that's going to allow us to set this thing equal to 0. And you don't necessarily have to write, you've probably noticed I've been writing this step on every single problem. If you're at a point where you could just do that in your head, that's fine, as long as you do it right. So there we go, we've got our equation that we are going to solve. We're looking for the x values that make this true, and we're going to use the graphing technique to do so. Okay, so back to the calculator. Let's make sure I'm not covering anything up here. I think we're good. So let's see here. Y equals, clear out the last one, and here we've got x squared minus 2x plus 6. I'm going to look at the table, and we're going to start, let's start throwing some numbers in here. Let's start with 0, 6. Oh, not much is going to fit here. 1, 5. I think you could probably see what's going to happen here. 2, 6. And then 3, 9. We're already way off the grid, so I mean it's not even really worth writing these down. But let's see what we can draw on here. So we got 0, 6. You could probably tell what's going to happen here. This is going to be a case where we get no solutions. Right? The parabola is just way too high up. It never touches the x-axis. What that means is that there's no x value that could be put here or here that would make this true. Okay, so like at the very beginning of the problem, there's no x value that if I plug it into this x and this x that will get an equality. So unfortunately, we just get no solution here because there's no x-intercepts. All right, so we're going to look at a couple of some application problems. I think there's 2 of them, and I want to show you how to locate the x-intercepts in the calculator a little bit easier if they're not integers. In other words, if they're not intersecting the x-axis at a nice point on the grid, if it's like in between 2 and 3, we don't want to just estimate what they are just by looking at it. We want to be a little bit more precise, and I'll show you how to do that in the calculator. All right, so let's start with this football problem. It says a football player kicks a football 2 feet above the ground with an initial vertical velocity of 75 feet per second. This function represents the height in feet after t seconds. Find the height of the football after it is kicked. So h stands for height, t T stands for time. Okay, so basically what we want to do here is we're going to throw this equation in the calculator, plot as many points as we can find on here, and hopefully we can answer the questions. So back to our good friend, the calculator. Let's see here, turn that on, and let's get this slightly out of the way here. Okay, so I'm going to go to y equals, clear out the last one, and type in -16. Now, even though it says t, I'm still going to use this button, okay, x, comma t, comma theta, comma n. That's my independent variable button, so I still want to use that. X squared plus 75x plus 2. And let's look at that table, see what's going on. And we're going to start at 0 because nothing can happen before time equals 0. And because that's when he actually kicks the ball. Now you might be wondering, why do I start at 2? Well, he's basically holding the football 2 feet off the ground before he kicks it. So he's not kicking it off the ground. He's holding it, or it's somehow being elevated 2 feet when he kicks the ball. So let's plot as many of these points as we can on the graph. Let me move this over. So let's see, we've got 0, 2. Now hold on, this is looking like we're not going to be able to fit very many of these points on here. So what we may consider doing is changing the scale here, because look at how big these numbers get, 61, 88, 83. So what I'm going to do is, instead of this y-axis, which is representing height, what I want to do is change it so that this, instead of doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm going to go by tens. So like I'm going to say this is 10 instead of 1, and this is 20 instead of 2, and 30, 40, 50, and then we'll go all the way up to 100. I didn't write each one of those because that's going to take too long, but you get the idea here. So we're just going to rescale this. The time, I think, is fine. I don't think we have to change that at all. This is our time. Okay, so 2 is going to be way down here. Okay, then we got 1, 61, which is going to be roughly here. We're just kind of estimating where these points are. 2, 88, which is going to be almost up to 90. 3, 83, so now the football's starting to come down. 4, 46, this means somewhere right about here. And then 5, negative 23 is going to be like down here. So what that means is, since the ground is the x-axis here, we know we're going to hit the ground somewhere before t equals 5. Because at 5, we should be down here at negative 23. It means our parabola is going to hit that x-axis somewhere around here. So just, roughly, we've got a parabola that's going to go up, and then it's going to come back down, and then hit, let me try to get that to look a little nicer. We want to hit the ground before we hit t equals 5. So somewhere right around here. Now it looks like it's about 4.5, but this is a pretty rough sketch, and we don't want to just do a guess here. We want to try to be as accurate as possible, and that's what we're going to do here. So part A says find the height of the football after each second it was kicked. Essentially, they're just asking you to make a table here. So let me just do a real quick and dirty table here. So we've got T and we've got H. So, and the only ones I'm using here is T equals 0, 1, 2, 3, and 4, because it can't go below the ground, so I can't really use any other values. The height is going to be 2, 61, 88, 83, and 46. So those are just the points that we plotted on the graph. Use the results and the graphing calculator to estimate where the football hits the ground. Okay, so, or when the football hits the ground. So it's going to be in between 4 and 5. Let's take a look at the graph real quick over here, see what it looks like. Okay, so we see it goes a little bit off the grid. We could see, though, that the intersection point is happening, right in here. Okay, so To find this x value, you're going to do these steps. So, pay attention here. I'm going to take this slow. I'm going to hit second. I'm going to hit the trace button to access the calc menu because I hit second. So second calc. And I want to find the 0. Remember that these solutions can be called roots or zeros. So a 0 means the same thing. So I want to find the 0. And it's going to ask me a series of 3 questions. It's going to ask left bound, right bound, guess. So basically what you want to do is you just want to type in a number that's to the left of the x-intercept, a number that's to the right of the x-intercept, and then the guess can be basically any number that's in between those. Essentially what you're doing is you're just telling the calculator which x-intercept you want it to find. We don't care about this one that's negative something. We really only care about this one. So a number that is to the left of this is 1, 2, 3, 4. 4 is safe. And then to the right, we know 5 is to the right of that. So a good guess might be something like 4.5. And it'll give you the 0. Now this is a long decimal. You don't need to write every single decimal. So I'm just going to round to 2 decimal places here. And so it hits at 4.71 seconds. So let's go over those steps again. You're going to hit, in fact, let's do this. I'm going to be kind of fancy here and say second. Okay, so we want to hit that one. And then the calc button. Okay, so second calc, then you're going to go to 0 is going to be the next thing. And then you pick 3 numbers, okay? So the left bound is going to be a number to the left of the x-intercept, and that's up to you, okay? I mean, the closer you can get, the better, but it's not really like a huge deal, what number. If I would have picked 3, for instance, it still would have worked. The right bound, similarly, is a number to the right of the x-intercept. And then finally, it's going to ask you for a guess. That just needs to be something that's in between the left and right bound. So basically any number between the left and right bound. So those are the steps you can take in the calculator to get those x-intercepts. Sometimes it's easier just to graph it and find it. If it intersects at a number at 5, then you don't need to go through all this. But if the value's in between 2 integers, you're going to want to use this technique. Okay, so second calc 0, then you put your left bound, right bound guess, and go from there. So we'll see one more problem where we have to do that, but that's the basic idea. Number 12 says you throw a softball straight into the air. They give you a function to represent the height in terms of time. So we want to know first what's the maximum height of the ball, and after how many seconds will it hit the ground. So first, go to y equals. Clear out the last equation, and we're going to hit negative 16. Let's see, you probably can't see that. Let me just bring that down just a bit. Let's see. There we go. So you can see the equation. Hopefully you have this open on your end so you don't have to rely on what you're seeing here. So 16x squared plus 40t plus 5. Let's go to the table here, see what we're working with. So let's go ahead and plot what we can here. We'll start with 0, 5. Now, let's see. This one, it looks like it's getting upwards close to 30 here. So maybe instead of going by 5s, instead of going by 1s, let's go by 5s. So this would be 5, 10, 15. So we're just going to rescale this height axis. 20, 25, 30, And then, we really don't need to go anywhere past there because look at those numbers. It's going to peak out around 29. Okay, so let's plot what we've got. 0, 5, 1, 29, 2, 21. It's going to be, it looks like it's falling back down again. And then 3, -19 is going to be down here, so we know we're going to hit before that happens. So now look, this doesn't really look symmetrical, right? So that's because this is actually going to go back up a little bit more after we hit that at t equals 1. So the maximum height is not super obvious here. It's going to do something like this, right? And then we also want to know, like, when does this happen? So the question is going to be, what's the maximum height of the ball? In which case we are looking for this coordinate right here. And then when does it hit the ground? We're looking for this right here. So we're looking for the t values for that and that. So let's find the x-intercept first because that's what we did previously, and we can follow these instructions to get that. We're going to hit second, calc, go down to 0. We're going to pick a left bound. I'm going to pick 2. And let me move this a little bit more out of the way here. How am I going to fit all this? Let's see here. That's close enough. So my left bound, I'm going to pick 2. My right bound, I'm going to pick 3. And my guess, I'm going to pick 2.5. And so we get 2.6. I guess that rounds to 2.62. So when time is 2.62, it'll hit the ground. And then what's the maximum height of the ball? So we don't know how to do that yet, but we're going to do something very similar, okay? It's just that instead of doing, let's see if I can select all these? That'd be pretty sweet if I can. Nope. Okay, so it's not going to let me do that. So we're just going to copy this. Oops. No, let's see. Copy. There we go. So second, and we're still going to go to calc. Okay, but instead of selecting 0, we are going to select maximum, and that's going to help us find the maximum value. Okay, so let's see if I can get a little picture of that in here. We want the maximum. Okay, now the left and right bound, all that stuff is going to be basically the same. Let's see if I can just copy all that. There we go. You want to pick a number to the left of, instead of the x-intercept, we're going to do the maximum, and then a number to the right of the maximum. And we're talking about the t values here, which are going to run along that horizontal axis. I don't think I labeled that, but this is the t-axis or time. So, like for instance, we know that the left bound, a good left bound might be 1, and a good right bound might be 2, because we know that maximum's happening in between there. So let's do that. So second calc, we'll go down to maximum, use a left bound of 1 and a right bound of 2. My guess is just going to be 1.5 right in between there. And then you can see we get a maximum at 1.25 seconds. So that's pretty much it. So just to kind of recap what we did today. Let's get rid of that calculator just so we can kind of show everything at once. So yeah, today we looked at how to solve a quadratic equation using graphing. And it's a little bit easier when the graph actually hits the x-axis at an integer. But if it's not, you can use these little calculator tricks to make it work. But all you really need to remember, like the big idea from today, is that the solutions to a quadratic equation can be found by graphing the related function and identifying the x-intercepts. So if you find those x-intercepts, you've found the solutions. That's it for today. I know this has been a longer video than usual, but hopefully all this made sense to you. Let me know if there's anything I can do to clarify.